Okay, so today we will talk about what is affecting the boiling point of the element, and we will see particularly what is the effect of intermolecular forces in the boiling point, and we will see cases where the intermolecular forces in between is the same. Now keep in mind what we have said in terms of the intermolecular forces. Intermolecular forces are three types. We have London forces, which are the weakest one. We have dipole-dipole forces, and we have the hydrogen bond. So London forces is the temporary, we have said that is the temporary rearrangement of the electron in one atom, creating that temporary dipole moment. So then those London forces are in every compound, and we don't even have to think about it, but then we just have to write them what it is. Dipole is when we have dipole force between the dipole momentum between the two atoms, and the hydrogen bond is when we have hydrogen that is directly attached with oxygen, nitrogen, and fluorine. Okay, it's directly attached. So we even have seen the cases when we have the water that has all three forces, London force, dipole-dipole, because there is a difference on dipole moment of, it's a bend shape, so that there is a dipole net. And then we have the hydrogen bond, because hydrogen is connected directly with water. And then on the same breath, we have seen and we have discussed, even on the previous cases, on previous lessons, then when we have HCN, then we have only the two type of forces, London forces, which is present on everything, and dipole-dipole. We don't have hydrogen bonds, even though that we have hydrogen and nitrogen here, because those two are not directly bonded between each other. Okay, so now let's see what it is. We've said that intermolecular forces are forces that are within the molecule. So what is happening within the molecule? And then it is when we are boiling a substance, what we are doing is we are breaking the bonds between molecules, okay? So now the stronger the forces, the higher the boiling point. It makes sense. Because when in order to break a bond, we need to input more energy on it, meaning that the temperature will increase way more. So in this case, when we are, even when what we started the lesson today, so HCN and water. In the HCN, we will have London forces and we will have dipole-dipole forces. Versus in hydrogen or water, we will have all three forces. So we'll have London force, we'll have dipole-dipole, and we will have the hydrogen bond, as we discussed it even before. Therefore, water would have the higher boiling point because it has more intermolecular forces on it. And one of them is a very strong force. So now, if we can say that if a compound has more intermolecular forces than the other, compound, then compound A, let's say, has more intermolecular forces than another compound B, then compound A will have a higher boiling point than compound B. Okay, so if we see that in two compounds, one has more intermolecular forces, then we can say that this compound will have a higher boiling point. And theoretically, HCN has a boiling point of about 25.6 degrees Celsius versus water that has a boiling point of 100 degrees Celsius. And this is supporting what we said, that more intermolecular forces and more higher boiling point. Now, okay, when we have more intermolecular forces, then we have more higher boiling point. But what is happening when we have two compounds that have the same number of intermolecular and the same type of intermolecular forces? So when they have the same type of intermolecular forces, then the power goes to the number of electrons. The higher the number of electrons, that means that you need the interaction force in within the between the electrons is higher because there are more electrons on it. So therefore, it requires more energy to break it. So in the case of boron and fluorine, the only type of forces that we have here is London forces. We don't have any other type of forces. Dipole is equal to 0 because they are polyatomic molecules. So the difference between the electronegativity difference between the two is equal to 0. So then the only force that they are experiencing is London forces. Therefore, what do is we observe the number of electrons. And when we take a look at boron, then boron will have in total 70 electrons versus fluorine that will have in total 18 electrons. So then, obviously, to bring boron to the boiling point will require more energy in order to break the bonds between them. So then boron will be harder. Boiling point will be higher because it requires boron will have a higher boiling point because it requires more energy in comparison to fluorine to break the bonds. Okay, so when we have the same type of forces, in this case, we have the same type of forces because we know the order of the intermolecular forces goes, those are the three London forces, dipole forces, and then the third one is hydrogen bond. And the order goes, this is from the weakest to the strongest. And the weakest. So the weakest force is London forces. And then the strongest one is hydrogen bond. And somewhere in between is dipole. So if we have the same type of forces, let's say, in this case, London forces, or we have dipole, or we have hydrogen bond, then the power goes to the number of electrons. You have to see the higher the number of electrons, higher number of electrons will result into higher boiling point of that compound. So if you observe this graph here, and you will see this information is taken from the textbook. So you can refer this to the textbook, and then the graph will be something like this. So it's the boiling point of hydrogen compounds of elements in group 14 to 17. So you will see, and then this will be what is the graph that the hydrogen compounds of different elements in group 14 and 17 is happening. So when you plot that, this is the graph that you will see. However, when we see, then we observe the questions and say, why do hydrogen fluorine, and NH3 have significant higher boiling point? So we have here water, HC, and NH3 that have significant higher point, because what do they have is they have that is known as the hydrogen bond. We said that hydrogen bond is when hydrogen is directly connected, bonded with oxygen, nitrogen, and fluorine. And on this case is water is directly, the structural is like this. Hydrogen and fluorine, the structural diagram is like this. And nitrogen and hydrogen is like this. And we have lone pairs here. So then we see that hydrogen is directly connected, bonded with nitrogen, fluorine, and oxygen. Therefore, all those three will have the hydrogen bond. So the reason why is the fact that the force that they are experiencing is hydrogen bond, which, as we said, is the strongest force. And what do you notice happen to the boiling point as the molecules get bigger? Bigger meaning that more electrons, the boiling point will increase. Will increase because the power goes to the number of electrons as well, and it requires more energy to break the bonds between the atoms. Now, the last part of this lesson and the last part of bonding unit is talking about the properties of solids. So when we have a metallic bond, the electrons are shared across solids. So when we have any metal, think of any metal, iron, magnesium, or any metal, then what is happening is that the electrons are shared across the solid. So they are going, as you see here on this picture, even though that we have the electrons here, they are shared in between all the other protons or nucleuses, creating that is like a cloud of the electrons. Okay, so the reason why they are doing this and creating this is because then they are free to go. They are attracted to this particular nucleus, and then this electron, the electron in the outer shell of this nucleuses are attracted to another. So the repulsion and attraction of the electrons between the molecules of metals is happening consistently, creating that is known as the mobile electrons. Okay, so now the low electronegativity allows electrons to be mobile, to move from one nucleus to the other. And in this case, what is happening, metals or metallic compounds have some of those properties, like malleable, which means that can be bent, and you can give different shapes on it. Can be ductile, meaning that they will be deformed without losing the toughness. They are strong, okay? Toughness of them. And then good conductor. They can transmit, they can carry, they can conduct heat and electricity. Okay. Covalent crystals are formed by a network of covalent bonds. Okay, by a network of covalent bonds. For example, diamonds or graphites. They are both composed of carbon. They have the same structure. Okay, so the same composition, I should say. They are both formed. Base of them is carbon. However, different network will affect the strengths. Okay, different network will affect the strength of the molecule. This is the case when we have a diamond. So the way that it is formed is like they are connected like a pyramid. And what is happening with graphite is formed in a like plies, but they are between each other, so you can easily slip them. And diamond, you know what diamonds are. Graphite is, let's say, any pencil that you write, those mechanical pencils, those are easy to write. Why they are easy to write? Because the mark that they will leave on the paper is easy to be drawn in the paper. The mark is easy left on the paper because of the structure that they have, like plies or ply like sheets between each other. Okay, so now this is the end of this lesson, and you feel free to complete the assignment on that lesson. And if you have any question, then please ask in class. Also, what you have to keep in mind is you have to do the practice unit test bonding that is on D2L, and we will deal with a review on bonding, and then you will be able to write the unit test on bonding. All the best.